At the beginning of this century, materials like these did not exist. Nowadays, we use them all the time. In the home, we're surrounded by plastics and by man-made fibers. Whenever we sit or ride, at school, in the office, at play. In the shops, we take these foams and films, panels and paints, rubbers and resins very much for granted. The growth of our food may depend on the use of fertilizers and pesticides. Our health may benefit from new drugs, yet few of us can put a name to many of these materials. Collectively, however, they're often called petrochemicals, and that's because they're nearly all obtained from the processing of petroleum. When petroleum or crude oil is heated, different fractions distill over as the temperature rises. These fractions can be collected in different test tubes so that they're physically separated from each other. This process is performed on a much larger scale in refineries all over the world. A unit like this, for instance, would handle several million tons of oil each year. The various fractions coming out of the distillation plant need further treatment and purification before they can be used. Most of them are then used as fuels, often to provide power for various kinds of transport. Bitumen, waxes and lubricants are other important products. A small amount, perhaps 7 or 8% of the total, is used to produce petrochemicals. For most of these materials, the starting point is a fraction which overlaps petrol and kerosene. This mixture is known as naphtha, and we shall see how it can give us so many useful materials. The molecules in naphtha are all hydrocarbons. That is, they're made only from carbon atoms, shown in black, and hydrogen atoms, shown in white. Some will be straight chains, some will be branched. Others will be ring structures. The composition of the mixture will depend on the crude oil from which the naphtha was produced. The boiling point range will be from about 40 to 180 degrees Celsius. Petrochemicals can also be made from other starting materials. Hydrocarbon gas, for example, is often produced when oil is being extracted. In some parts of the world, there may be a great deal of it. This gas may contain ethane, C2H6, propane, C3H8, and butane, C4H10. If these are collected and separated, they too can be used to make petrochemicals. The key process is carried out in a plant such as this, a cracker. Inside a furnace, the naphtha or gas is heated to about 800 degrees Celsius by passing it through red-hot tubes. The large molecules are broken or cracked into smaller ones. This rearrangement of the molecules involves a chemical change, unlike fractional distillation, which is a physical separation. The main products, the molecules we need in order to make the materials we use, are ethene, propene, butene, and butadiene. These are all alkenes or olefins with one or more double bonds between some of the carbon atoms. The products may be stored in spheres like these. In industry, the compounds are usually called ethylene, propylene, and butylene. The petrochemicals industry has grown very quickly in the last 30 years, and huge plants have been built. It plays an important part in the trade of many countries. As we've seen, the industry starts with a process of breaking down hydrocarbon molecules. The pieces are then rejoined to build up new molecules. Often these are long chains which may be represented by single lines. Some of the ways this building up can be done will be considered in the rest of this series. In this part, we shall be looking at materials known as polymers. Many of these are familiar to us in the form of synthetic fibers or plastics. At first glance, we may often think that all plastics are very similar materials, but in fact their properties vary widely. For instance, a hot nail will slice through some plastics very easily. Others won't be affected at all. Let's see what gives rise to these differences. A polymer is formed when thousands of small molecules, or monomers, link up to form one giant molecule. This is called polymerization, and there are various ways it can happen. The simplest method can be illustrated by ethene, C2H4. Consider two molecules alongside each other. The double bond between the two carbon atoms is a reactive link. Under the right conditions, it'll break and connect with another molecule. This is addition polymerization, and here the monomers are all identical. The reaction can continue until a long chain has been formed containing thousands of ethene molecules. This is polyethene, also known as polyethylene. If we take ethene and treat it with chlorine, we can produce dichloroethane. This can be further treated to produce chloroethene. This will also undergo addition polymerization to form polychloroethene, shown here for simplicity with all the chlorines on the same side of the chain. This is another very useful polymer, also known as polyvinyl chloride, PVC. Phenylethene is another monomer which polymerizes like this. This polymer is also known as polystyrene. All monomers which polymerize by addition have a double bond between two carbon atoms. With all polymers of this type, the molecules, shown here as long chains, are linked only by weak forces of attraction between them. So when the plastic is heated, the molecules separate easily and the material softens and flows. Because of this, it's called a thermoplastic polymer. When the material is cooled down, it becomes rigid again. So the material which was affected by the hot nail was a thermoplastic polymer. It's a property which is very important when we come to make things out of plastic. Nylon and several other important plastics polymerize in a different way by condensation. For nylon, there are two monomers involved, with the colored boxes representing different hydrocarbon chains. One molecule has two NH2 or amine groups. The other has two carboxylic acid groups, COOH. An amine and an acid group react, eliminating water. The new molecule still has reactive groups at each end, so more monomers can add on. This polyamide is known as nylon. One form of it can be made quite easily in the laboratory. The material known as polyester is also formed by this sort of polymerization. Many condensation polymers are thermoplastics, but some behave very differently. The handle of this iron, for example, is made from a polymer built up from phenol, shown on the left, and methanol. These molecules can link to form chains as before. However, the chains also have reactive side groups which can link with more molecules. So we get cross-linkages and a three-dimensional network is built up. The whole polymer is really one giant molecule. Once it's been formed and shaped, a polymer of this type will not soften again on heating. This kind of plastic is known as thermosetting. Polyurethane, used extensively in foams for insulation and for upholstery, is another polymer of this type. So, learning about the structures of these molecules can often help us to understand why they behave as they do. It can also help to decide which plastic to use for a particular task. In a plastic kettle, for instance, what sort of properties is the polymer going to need? We shall see some other ways in which polymers are used commercially in the next part. Polymer molecules may be built up either by addition reactions, as with polyethylene, or by condensation reactions, as with nylon. Starting with ethene, the petrochemicals industry produces polyethylene, polychloroethene, and polyphenol ethene in large quantities, the last two shown in simplified form. From propene we get polypropene, another plastic produced on a large scale. So large plants are needed to produce the polymers economically. Some reactions may require high temperatures and pressures. All involve the use of catalysts. Here the polymer is first extruded, that is, pushed out through a row of small holes as a hot, sticky thread. After cooling in a water bath, the threads enter a dicer where they're chopped into tiny pieces. Other polymers may first be produced as a powder or as larger granules. From the plant, the polymer must be distributed to the various factories where it will be used to make things. Some will be sent out in bags like these, and a great deal is delivered in bulk tankers. At the factories where the polymer is to be used, it may first be mixed with dyes and various other chemicals. These will alter the properties to make the plastic more suitable for the particular application. Then the mixture will go through one or more shaping or moulding processes. Here a roll of flat sheet is being produced. These processes all involve heating the polymer to make it flow more easily, followed by forcing it into a particular shape. Extrusion of tubing or sheet which can then be further shaped, blow moulding for bottles and hollow objects, injection moulding, the forcing of the plastic into a precisely formed mould, vacuum forming, where the plastic is sucked into shape. These and other methods can produce objects large or small with shapes that are simple or complex. How a plastic behaves depends on its composition, and this in turn is affected by the way the polymer was originally produced. Take polyethylene again. If the molecules have a lot of side branches, the chains cannot pack very closely. So in this low-density polyethylene, the forces attracting the chains to each other are weak. To make them move apart needs very little energy, and this polyethylene softens at a fairly low temperature. But if we make the polymer so that these side branches are very short, the molecules can pack closely together and more energy is needed to separate them. Higher temperatures must be reached before this high-density polyethylene begins to soften. So this material can be used in many applications for which low-density polyethylene would be unsuitable. There are many other ways in which the raw polymers can be treated to increase their usefulness. Films of various types of plastics are produced in a range of thicknesses. Their uses may run from packaging food to covering greenhouses. Many industries use large quantities of plastics of various kinds. For building, packaging, furniture, transportation. If you look around you, you'll find many other examples too. Synthetic fibers are another important class of product for which many polymers are now used. Nylon, for example, can be used to make solid objects or drawn out into long threads. Polypropylene can be treated the same way. Not all plastics are suitable. Once again, it depends on the structure of the polymer molecule. The chains must be long, with little branching and no bulky side groups. This means there'll be crystalline regions, areas where there is a close-packed, orderly arrangement of molecules. These give the polymer strength when it's stretched into a fiber. These fibers can be spun and woven in much the same way as natural fibers, but their properties may be quite different. They may be more hard-wearing, for instance. Many fabrics used for clothing or domestic purposes are often mixtures of synthetic and natural fibers. The other main group of important polymers are the synthetic rubbers. Large amounts are produced and used instead of or in combination with the natural material. The polymer of buta-1,3-diene, for instance, is one of the most widely used. All these polymers we've seen, and the many others not shown but also important, have been the most striking contribution of the petrochemicals industry. In total, they account for about 70% of petrochemicals production. They're now widely used all over the world. Sometimes they relieve the pressure on natural materials like wood, rubber, or metal. More often, they've given designers and engineers the chance to develop new applications or give products better qualities. They may make things stronger. more resistant to wear or corrosion, lighter or less expensive to produce. They represent a remarkable achievement by the chemists and engineers who've helped to develop them. While a great deal of the petrochemicals produced end up in polymers of one type or another, there are many other important products. There are various chemicals generally known as solvents, for example. That is, they dissolve things. Here the solvent will remove any dirt or grease that may be sticking to these pieces of metal. The plastic balls on the surface help to prevent the liquid evaporating. Other solvents can help to hold dye or ink in solution, making it easier to use for dyeing or printing. Such chemicals have helped improve the dyeing of fabrics of all kinds. Many solvents are made with ethene as their starting point. By adding oxygen, we get epoxy-ethane. And by adding alcohols to this, we can build up whole families of compounds that are used as solvents. This is one of the most widely used of all solvents, propanone, still commonly called acetone. The starting material is propene, produced by cracking naphtha or natural gas. From this we can produce propan-2-ol and then propanone. Solvents may be chosen because they're able to perform various useful tasks, stripping paint from a surface or grease from hands. In this case, the chemicals used must be gentle to the skin. For paints and other surface coatings, the choice of the right solvent is very important. It must keep the materials evenly mixed together until they're used. Once the paint is put on, however, the solvent must evaporate evenly, leaving a smooth film of paint on the surface. Detergents are another group of compounds with a difficult job to do. Detergents and soap are both cleansing agents and work in the same way. Water alone does not wet surfaces well because the water molecules are strongly attracted to each other. So the water is held tightly together in small drops. When detergent is added, however, the water spreads out, wetting the surface properly. This is because the detergent molecules have a head which is water-loving or hydrophilic, and a tail which likes grease or fat, that is, lipophilic. When they enter the drop of water, the molecules spread around the surface with their tails trying to avoid contact with the water. This reduces the attraction between the surface water molecules, known as surface tension, so the water spreads across the surface. Suppose the fibers of a piece of clothing are soiled by grease or oil. The tails of the detergent molecules are attracted by it. The heads stick out and attract water molecules, helping them to penetrate between the grease and the fabric. So the grease is gradually detached from the surface and is completely surrounded by detergent molecules. This process can be seen here using oil which has been colored red to make it show up better. Detergents have other important properties too. Normally, oil and water do not mix. The oil forms a separate layer on top of the water. But if we add detergent, an emulsion is formed. That is, the oil is held in tiny drops spread throughout the water. So any oil or grease removed from clothing would be prevented from sticking to it again. Particles of dirt can be dealt with in a similar way. The detergent keeps them suspended, so that they don't settle again or combine into larger lumps. Soap molecules have a tail which consists of a hydrocarbon chain with about 12 carbon atoms. The head contains a carboxylate group, which is an anion with a negative charge. But in hard water, where many calcium or magnesium ions are present, soaps have the disadvantage that the ions form an insoluble scum. This wastes a lot of soap, as well as being unpleasant. Detergents avoid this problem, although their molecule has a structure very similar to that of soap. The tail is again an alkyl chain with 11 or 12 carbon atoms, and this is joined to a benzene ring, with a sulfonate group attached. This too is an anion. These are the commonest types of detergent produced. Both the hydrocarbon chain and the benzene come from fractions produced in the refinery. As well as detergents and solvents, the petrochemicals industry produces many thousands of useful compounds. These are generally described as industrial chemicals, and they find a great number of applications. From epoxy ethane, for instance, we can make ethane 1,2-diol, also known as ethylene glycol. When added to water, a mixture is formed with a lower freezing point than water alone. So in cold climates, the compound is used as antifreeze and prevents engine cooling water from freezing in the winter. The pharmaceutical industry is another which makes use of petrochemicals. They may be the starting material from which the active ingredient of a drug is made, or they may be used as solvents. One other aspect of life in which petrochemicals are important is in agriculture, and we shall see how in the next part. One of the most important problems facing the world is to grow enough food. In many countries, large numbers of people already go hungry, and the population continues to increase. In some areas, the amount that can be grown is limited by the climate, but there are other factors which can have an important effect. It's on some of these factors that the work of the scientist can have an influence. Research has shown that, along with sunshine and water, one of the main requirements for the growth of most crops is a supply of nitrogen in a form that the plant can use. Without it, the plant is less able to build up protein. In the past, this nitrogen would have been provided in the form of natural fertilizer, manure of various kinds, for instance, and this can still play an important part. But as agriculture has developed on a large scale, these natural sources are no longer enough. So man-made, inorganic fertilizers have been produced to fill the gap. Many farmers now rely on these to help them to grow more. These nitrogen-containing fertilizers are usually made from petrochemicals, so the manufacturing often occurs next to a petrochemicals plant. The starting materials are nitrogen from the air and hydrogen obtained during the cracking of naphtha or hydrocarbon gases. These are combined to form ammonia, NH3. Sometimes this may be used directly by injecting it into the soil. Most of the ammonia produced is converted into other compounds, however. With carbon dioxide, under certain conditions, the ammonia reacts to produce urea. This contains 40% nitrogen and is widely used as a fertilizer. By converting some of the ammonia to nitric acid and reacting this with more ammonia, we can produce ammonium nitrate. This contains a high proportion of nitrogen and is one of the most popular nitrogen-bearing fertilizers in use at the moment. These fertilizers can have a big effect on the yield of a crop, provided they're used correctly. Too much can be as bad as too little. Their value has been proved on many kinds of crop in climates of all types. Increasing yields in this way is not much use if the only ones to benefit are insects or other pests who also feed on the crops. There are many thousands of species which attack our food supplies in this way. Nor is it helpful if the weeds also flourish and compete with the crops for the nutrients in the soil. So chemists have developed various chemicals which help ensure that the crops survive to reach the human population for whom they were intended. Fungicides are used to kill fungi which may threaten cereal crops, vegetables and fruit. Herbicides are used to kill weeds. Some will kill all weeds with which they come into contact. Others are very selective in their action. Here, for instance, killing the wild oats, but not the barley. Such chemicals may have quite complex molecules which have been built up in a particular way to produce the effect required. Insecticides are used in a similar manner to kill insects which attack food and other important crops such as cotton and tobacco. It is a vital and often a spectacular battle. Locusts, for instance, can strip vast areas of all plant material in a very short space of time. In Africa especially, they are a terrible threat. Many other insects and pests can either eat the crop totally or so damage the plants that they cannot grow properly. One of the first groups of compounds to be used in this battle were the chlorinated hydrocarbons. DDT was perhaps the most well-known of these, although it's not used much any longer. More recent discoveries, such as the pyrethroids, may now be employed instead. These and other new pesticides have been of great benefit to farmers and food growers of all kinds. Such chemicals have also helped greatly in the fight against those diseases which are partly carried by insects or other creatures. The chances of catching malaria, typhus, bilharzia and other diseases has been reduced in many parts of the world thanks to their use. They also help to keep livestock healthy by fighting mites, ticks and other parasites. Developing compounds like this is a very long and costly business. Many thousands of molecules are studied. Those with promise have to pass through a careful screening program. Apart from checking their ability to kill pests, these tests study whether the chemical is going to have any harmful effects on other animal or human life. As with all chemicals, correct use is very important. The right concentrations should be employed, and if necessary, the people involved should wear protective clothing. No harmful materials should be left lying about to create a risk for someone else. The use of these and other products of the petrochemicals industry has generally had a good effect. More food has been grown, the standard of health has risen, new industries have been created. But sometimes there have also been problems, and these have been used to question the links between the chemical industry and society as a whole. We shall consider this in more detail in the final part. The petrochemicals industry now produces a wide range of products that are part of everyday life for millions of people all over the world. Whether they're plastics or herbicides, the chemicals involved have often been given molecular structures which suit them for particular tasks. The industry has developed these skills and grown to its present huge size from almost nothing in only 30 years. This is a remarkable achievement, yet it has not been totally trouble-free. First, there may be an effect on the local environment. As with many other industrial processes, people living nearby can be upset by noise and smoke, by smells, flares and so on. Those working at the plants have also had causes for alarm. Fires or explosions have sometimes occurred when operating conditions have, for some reason, gone badly wrong. With some chemicals, even tiny quantities can be harmful if the workers are exposed to them for long periods. If they don't understand clearly what these chemicals can do, users of the products, too, may face hazards. And there are occasions when the community at large can be affected. Some of the early pesticides, such as DDT, had molecules which did not break down very quickly after use. This prolonged their activity against the pest, but it also meant that the chemical could build up in birds or other creatures which fed on the pest and cause them harm. Such residues could also accumulate in humans. Many plastics materials, too, are difficult to break down by natural means, so disposal of waste can be a problem. Against these and other difficulties, we must also consider some of the benefits. If we had no fertilizers and pesticides, food supplies would be much reduced and many more millions would be facing starvation. The fight against malaria and other diseases and the development of more effective drugs have both gained from the products of the petrochemical industry. The result in many areas has been to raise the standard of health. The use of plastics and synthetic fibers has created new products and new industries and has relieved the pressure on some of our natural resources. As with many aspects of modern life, there is a delicate balance between good and bad. Individually, for example, the motor car provides greater mobility and convenience. Collectively, it can bring congestion and pollution. Whether it's cars or chemistry, we all need to make sure that the balance is as favorable as possible. At the chemical plants, more effective steps are being taken to reduce any disturbance to the local population. Additional soundproofing round the motors on the right, for instance, to reduce the noise levels nearby. More advanced control systems may help to prevent circumstances arising that could lead to accidents. Detection systems have also been made much more sensitive. These will monitor any escape of toxic chemicals and provide a warning well before a harmful level is reached. Protection for employees involved in potentially hazardous work is continually being improved. And safety appliances and systems are tested regularly. Such measures are all helping to improve plant safety and reduce any risk to employees and the local community. And in the laboratory, there is continuing research to make the processes and the products even less of a hazard. Research on pesticides, for instance. If the molecular structure is altered slightly, will the residues on the soil break down more quickly and so build up less in the earthworms? There's also research for the longer-term future. How best can we use coal as a source material for fuel and chemicals so that a supply is still available when oil and gas resources are no longer sufficient? Yet research, whether on processes like this or on individual chemicals, can never predict all the problems that could arise. Whether it's chemistry, the use of nuclear power to generate electricity, or any other new development in science and technology, there may well be difficulties, some known about and considered in advance, others unexpected. But these should not prevent us from following up new ideas. The benefits from many chemical discoveries have been enormous and wide-reaching. What we have to ensure is that the balance between risk and progress is a favorable one. The more people can gain some understanding of science and what it can achieve, the better the chance that some of the problems may be avoided in the future.